It has a serial communication through two wires, RxD and TxD, and follows a UART protocol. Um, UART protocol. There are two protocols, asynchronous and synchronous communications, and this protocol comes from RS-232 standards. And these standards are use only RxD and TxD two wires. RxD is for receiving data and TxD is to transmit data. So when we are saying asynchronous, that means at a time transmitting as well as receiving is carried out simultaneously. So we call it as a asynchronous or UART protocol. As well as not only these things, there are various things which should be considered in this protocol, how it behaves, what it does, and how data is transmitted. That we'll see whenever we go to the serial communication part of our lectures. Next is it requires an external crystal oscillator in the range 1 megahertz to 20 megahertz for its internal timing generation. 1 megahertz is the minimum and 20 megahertz is the maximum, the type of crystal which we can connect to this 8051. We cannot go less than 1 megahertz because the RAM used here is a DRAM and DRAM requires a refreshing. So that refreshing cannot be achieved if you give crystal frequency less than 1 megahertz. Whereas you cannot go above 20 megahertz because these are the limitations for digital circuits, because they need some time to rise from 0 to 1 level, or they need some fall time to fall from high, that is logic 1 to logic zeros. So including that, um, that's why the 20 megahertz limit is there. You cannot change it. If you change it, then the data or the accessing will be not proper. So these were the features which we had seen last time, as well as we had seen how the Harvard and von Neumann architecture behaves. Harvard architecture has separate memories, code and data. So whenever there is a separate memory, then each memory requires a address bus. These are the two address buses, and it requires a separate data bus for each memory. So two address buses and two data buses are required in Harvard architecture. Whereas if you go for von Neumann architecture, only one address bus and only one data bus is required to access the memory. So this is about Harvard and von Neumann architecture. Now we'll go to the architecture of 8051, how it is and what it is. So we'll start now our session of architecture. First, we'll see that arithmetic and logic unit. As I told you, this is a 8-bit controller. That means your ELU can operate on 8-bit data at a time. That means what? It can add, subtract, multiply, divide 8-bit data at a time. It cannot have 16-bit addition in one cycle. If you want to do, you can do it, but by using two processes, you can do that. But ALU at a time can do only um, two 8-bit data operations. So that data can be from A register and B register. There are two registers, A and B, though A is more popular or more efficient register as it is used to store the result of the ELU operation also. That's why A register, also called as an accumulator. Whereas B register is can be used in specific operation, just like in multiply and divide operation. This B register use. Otherwise, you can use for general data storage also. As well as with this ALU is connected a PSW or program status word. This is an SFR, special function register. There are special function registers in this. Each register is mentioned, but we'll do that. PSW is program status word, or also called as a flag register, or also called as a status register. So in some controllers, you will get that name as flag register. In some controllers, you will, or processors, you will find that is named as a status register. What this PSW has is the carry flag, or auxiliary carry flag, or um, overflow flag, or parity flag. All these flags are present in these locations. So PSW, program status word. All these A register, B register, PSW are connected through 8-bit data on address bus. So this bus is an 8-bit bus, not a 16-bit bus. So this bus is further connected to our internal RAM. which is of 128 bytes. And that RAM also contains a special function registers, or in short, we call it as a SFRs. How much RAM internal we have? We are having 128 bytes of internal RAM. So that RAM and special function registers are mapped in this area. So whenever we are going to access special function register, we have to go through this route only. So this 8-bit bus is also connected to ROM, that is a code memory. So whenever it is accessing a code or some data from the ROM, that is a code memory that can be accessed through this bus. Secondly, we'll come to that later on. This bus is further connected to 4 ports. As I told you, we are having 32 I/O ports, and those 32 I/O ports are grouped into 4 8-bit ports, and those are port 0, port 1, port 2, and port 3. Each are having 8 pins, and those pins are I/O pins. So 8 pins here, 8 pins here, 8 pins here, 8 pins here. So totally 32 I/O ports we are having. Um, Secondly, mm, somebody's mic is not muted. You can mute the mic if you are not using it, so that there will be no disturbances. So this bus is connected to latches, and these latches are connected further to ports. Now, what is latch and why we need it? So latch is something like a 8-bit data storage type. Now, how it is, whenever we give some data to port 0, that will be latched or stored in this latch and will continue giving that data to the port 0. Unless and until you don't give next data to this port, till that time the latch will hold the previous data. So whenever we give next data, the previous data will be wiped out and the next data will be stored, and it will provide that data to the port. So similarly, we are having latches to input of each of these ports. Port 0 has a latch, port 1 has a latch, port 2 has a latch, and port 3 also has a latch. So latches are used to hold the data until next data is received. So these are the latches. Um, Secondly, we'll come to this 16-bit address bus. Now, this 16-bit address bus is connected to PC. PC, in short, it is called as a program counter. So, as I told you, program counter and DPTR, these are the two 16-bit registers. Program counter is used always to point the code memory, whether that code memory is internal or whether that code memory is external to this IC. All these are accessed by PC, and that code memory, whenever as per the definition, always points to the next instruction to be fetched from the code memory. So PC always generates a 16-bit address of the memory location, that is the code memory location. Similarly, DPTR is also a 16-bit register, but is used to point only to the data memory. So that's why it is called, named as a data pointer. In short, it is DPTR. But we are having one more facility in DPTR, and that is uh, two 8-bit registers make one DPTR. So if you want to access DPTR, you have to access DPH separately and DPL separately. DPH is data pointers higher byte, and DPL is data pointers lower byte. So byte, that means 8-bit here, 8-bit here. So totally it becomes a 16-bit. And DPTR totally can be, if you address DPTR, then that will be a 16-bit register. If you address DPH, that will be only 8-bit register. So again, these two SFRs we call, they can be used for simple data storage also, and that's why they are also connected to 8-bit data and address bus here. That's why they are connected here. Otherwise, DPTR and PC always gives out addresses. PC gives out addresses to the code memory, whereas DPTR gives addresses for the data memory. This bus is further connected to ROM. We are having ROM of 4 KB. 4 KB, that means we are having 12 address buses. So those 12 address buses are connected to this internal ROM or internal code memory. As we are having code memory and data memory separate, that's why it is named as a Harvard architecture. So this is where you have to store the code or your program. So whenever I say code, that means it just means a program, whatever we have written, that should be stored in this memory. This bus is further connected to only two ports, that is port 0 and port 2. So port 0 and port 2, why they are connected? Because whenever we are going to access external code or data memory, then external I'm saying, then that code and data memory address should go outside, that is outside of this chip, and that goes outside on these ports, port 0 and port 2. That's why port 0 is a multiplex. Whenever I say multiplex, that means they will be functioning more than one more than one data. That means if they can be either used as a IOs, or they can be used as a A0 to A7 address bus, or they can be used as a D0 to D7 data bus. So one pin can be used for multiple application or operations. That's why we call it as a multiplexed pins. So depend when to use what, we'll see that too. But this port 0, all ports are IO ports. You can see here, IO here, IO here, IO here, IO here. If you are not using as a external address or data bus, then the same ports will be used as a IOs, that is input and output ports. Port 1 is not multiplexed, it has only IOs. So either you can use as an input port, output port, input port, output port, input port, whichever you want to use it as, or all 8 as output or all 8 as input. It depends on up to the programmer how he's going to use this. Then is port 2. Again, this is multiplex. It can be used as a IO port, as well as it can be used as a higher byte address bus. So whenever we say A here, A to A15, that means A represents address and D represents data. So address bus higher byte, that means A to A15 is 16 bit, 8 bit. So this 8 bit data address can be given out. Similarly, lower 8-bit A0 to A7 will be given out, and this addresses can be given either to the code memory or data memory, depends on the program what we are written. So whenever it is going to the code memory, then PC will give address to these two ports. Whenever you are accessing data memory, then DPTR will give address to these ports, port 0 and port 2, and both are 16-bit. That's why we are having 8 pins here, 8 pins here. Total becomes 16 pins. Okay, so this is about a port 2. Then is a port 3. Now port 3 is also multiplexed, and by default function is as a IO, input and output port. Rest it has other functions also. 2 pins out of that are used for external interrupt, which are INT 0 bar and INT 1 bar. 2 pins out of this are used as a counter input pins. That means we are having two 16-bit counters, and for that counters we need external pulses, and those external pulses are 2 pins are used to take in those external pulses, and those 2 pins are T0 and T1. So 2 pins for counter. Then 2 pins out of this port 3 are used for serial data. That means those 2 pins are named as RxD and TXD. So those 2 pins, so 6 pins are used here. Whereas 2 pins out of this are used as a read bar and a write bar signal. So 1 pin for read bar and other pin for write bar. So why we require this read bar and write bar signals? These two signals are required whenever we are going to access data memory. So whenever we are accessing data memory, accessing, that means either taking in or writing something to that data memory. If you are writing something to that data memory, then WR bar will go low. And if you are reading something from data memory, that is reading, that means taking inside, and writing, that means giving out. So whenever you are reading something from data memory, then this read bar signal will go low. So read bar and write bar, these two are the control signals which are used to access external data memory. So this part I hope you have understood. 1, 2, 3, 4, 4 into 8, 32 pins are used here. Rest 8 pins are here which are used. We'll see those pins. So this block actually is the brain of the controller where it controls everything. What it controls the system timings, it looks into interrupts, timers, it looks into data buffers and memory control. So all this brain is used here. So this we can't call it as a timing and control circuit also. So what all the pins are connected here, which are again 8 pins. So total we are having 40 pin IC, 32 here and 8 here. That becomes total 40 pin IC. So what are these pins? We'll see. First is EA bar, named as external access bar. Now, what is this pin used for? Very simple. Whenever this pin is grounded or this pin is connected to ground, then by default, whatever data generated by PC will only be going outside. That means to fetch data or code from external memory. Again, I am repeating the same sentence. See, if this pin is connected to ground, then whatever address generated by PC will access only external memory and not internal memory. Getting this? So there should be some memory connected at the uh, outside of this controller, which will be accessed by PC. And at that time only you have to connect EA bar to ground. So if you are connected this EA bar to VCC, then what? Then this PC will only access internal memory, will not access external memory at all. That means you will not get address data or address here on these pins at all. So normal operation, well, until and unless we don't require more than 4 KB of memory space, till that time this EA bar is connected to VCC. So it will not give out some erroneous data which tries to access the external memory because we haven't connected any external memory here. So always remember this EA bar should be connected to VCC if you are not accessing external memory specifically. Next is ALE, address latch enable. Now, as I told you, A bar either connect to VCC or ground depending on your application. ELE will only come into picture if this EA bar is connected to ground. Now, how it comes to picture and what it says? ELE is the long form of that is address latch enable. So you'll see here in port 0. What we are having here is port 0 has two things. One is that it will uh, uh, give out address on this port pins as well as same 8 port pins or same 8 pins will be used to take in or give out data. So on the same pins you are having address also, and on the same pins you are having data also. So how to differentiate between them? So that is differentiation is done by controller by giving by making a time division multiplexing. That means what? At the starting of the clock pulse, it will give out only address and it will not give or take in data. So during whenever it is going giving out address, at that time ELE signal will go high, and before removing address from that ELE signal will go low, and the same pins will be used to take in or give out data from the same 8 pins. So that's why whenever there is a multiplexed address data bus, in all controllers or processors, always this ALE signal is used with the same name. Remember, with the same name, ALE. With the same name, Intel uses this ALE name whenever there is a multiplexed address data bus. So multiplexed address data bus, that means address also and data also on same 8 pins, and during that time only ALE will be used. So if you are going to access or if you are going to connect some external memory, at that time you have to use this ALE signal as well as some hardware, that is some external IC called as a latch IC at this port, so that you can separate out address and data. We'll see in the next part how we are separating that. Next is PSEN, called as a program store enable. This pin. Now, as I told you, this follows an Harvard architecture. That means um, if you are connecting external memory, then there will be two separate memories. One should be a code memory and other should be a data memory. So whenever you're accessing memory, then that memory you're going to read or write something you have to do, right? So to access data memory, these are the two control signals, and to access code memory, this is the signal called as a PSEN, program store enable. So when this signal goes high, that time the data from the code memory will be coming in. Remember, data from the code memory will be coming in. So PSEN is similar to read bar, but the only difference is that this signal will be only generated whenever your controller is accessing external code memory. Getting this? So PSEN, program store enable pin. Next two pins are uh, XTAL1 and XTAL2. These are two with the name Crystal 1, Crystal 2. Across these two pins, you have to connect a crystal oscillator with the two capacitors. We'll see those connections also. And that crystal oscillator should be in the range of 1 megahertz to 20 megahertz only. So across these two pins, you have to connect external crystal oscillator. Next pin is a reset, RESET. This is um, active high signal. So whenever you give active high signal to this IC on the pin reset, then the whole IC chip will reset. That means what? PC contents will become 000 or 0. That means it will start accessing program from 0000H location. Contents of A register, contents of B register, contents of PSW register will become zeros. So that means you are going to restart all these things. RAM contents will not change, ROM contents will not change, and all these ports will start acting as a input ports. So remember what happens whenever a active high signal is given on this reset pin. So we have to connect one circuit for the reset also. We'll see that in our session. Next is VCC and ground. It requires plus 5 volt as a power supply and a ground. So this is what the pins are and also the internal architecture of 8051. Okay. Um, some things are shown here also. Those are SFR, special function registers. So SFRs, just name we are given here, but what all those SFRs are present are shown here. So IE, IP, PCON, SBUF, SCON, PCON, PMOD, PL0, PL0, PL1, and PH1. These are the short forms used, but what they mean, IE, that is interrupt enable SFR, IP is interrupt priority SFR, PCON is power control SFR, SBUF is serial buffer register, SCON is serial control SFR, TCON is timer control SFR, T-mod is timer mode selection SFR. TL0, TH0 are two 88-bit, 16-bit timer 0, and TL1 and TH1 are two 88-bit for timer 1. So these are the SFRs. Each and every one will study in details because they are not only 1 byte, but their bits are more important because their bit control the operation of this controller. So we'll see these details later on in our session. Whereas this is internal RAM shown, which has bank 0, bank 1, bank 2, and bank 3, and rest 80 bytes, and 80 bytes are for scratchpad, and 16 bytes are for bit addressable area. That also we'll see in the later section. So This is about the architecture of 8051. Now I'll ask all of you to ask some questions what we haven't understood. Yes.
Hello.
Yeah.
This two architecture is there, na? Harvard and one Neumann.
Yes.
So which one is better?
Okay. Um, as compared to Harvard and von Neumann architecture, I'll show you those architectures here. So these are the two architectures, Harvard and von Neumann architecture. Which one is better? So for that, it requires a lot many things. So let us see differentiate first. Whenever I say Harvard architecture, that means it has two separate memories. One is code memory and the other is data memory. So whereas in von Neumann, total memory is at one location only. Whether you want to have code memory or data memory, that will be only one memory. So von Neumann has only address bus to access memory and data bus to take in or give data in this memory. So you don't require more address buses. Address buses, that means a bunch of wires, let us say. So only two parts of this buses we need whenever we are going to access one email. So this type of architecture is best suited whenever we are having microprocessors, because you must have knowing about 8085, 8086, 80386, 80486, Pentium 4, Pentium 5, and then i3, i5, all these architectures, they follow this von Neumann architecture. Why and how? See, you must be having laptop PCs, and laptop PCs, some are having 4 GB RAM, some are having 8 GB RAM, some are having 1 GB RAM. So those processors need to connect external memory. So whenever you need to connect some external memory, then von Neumann architecture is preferred. Why? Because the board size does not increase because you have only one address bus and one data bus. But if you try to have a Harvard architecture with the similar one, then your board size will increase because here we are having one, two, three, four bunch of wires, two address buses and two data buses. So your bus size will go on increasing. So here, von Neumann architecture has an advantage. Secondly, what about Harvard architecture? Harvard architecture is preferred whenever you are having memory internally or inbuilt into an IC chip. So whenever it is inbuilt into an IC chip, you don't need to connect some external memory. So in that cases, this is best. How it is best? Because simultaneously I can access code also and data also in one cycle, and that makes your processing faster. But only disadvantage is that the memory should be internal. Otherwise, if you connect external memory, then the board size will go on increase. So these are the basic two differences between Harvard and von Neumann. So which one to prefer depends on your application. Have you understood?
But in Harvard, we can access code and data simultaneously at the same time.
Yes, at the same time you can access.
But this one Neumann only we can access only one, maybe
Yeah,
code
because
or
there is only data bus, only one data bus. So either you have to take in data or you have to take in the code.
okay. So this Harvard architecture maybe work fast.
Yeah, if it is connected internally, it has a limitation that if you cannot have more memory, if you want to have more memory, then your board size will go on increasing because you have to give this one, two, three, four buses external. Got it?
Okay.
Okay. So any other question?
This clock frequency why require 1 megahertz minimum?
Because in the features we had seen, It has a DRAM, the RAM, whatever 128 bytes we are having. It has a DRAM. DRAM, that means dynamic RAM. There are two types of RAM. One is SRAM, that is called as static RAM, and other is called as a DRAM or dynamic RAM. Static RAM is made up of flip-flops. So if your powered up that memory, that is SRAM, is powered up, that means you are given supply. So if it is powered up and you have asked the SRAM or you have stored something in the SRAM, then that value, whatever you have stored, will remain there until and unless for 1 day, 2 day, 3 day, 4 day, until and unless you don't remove the power till that time, the data will be available in the SRAM. But the case is different for DRAM. DRAM is made up by the one of the MOSFET and a capacitor. So capacitors are used to hold the charge. So if you want to ask him to hold a logic 1, that means you um, charge that capacitor and keep it at 5 volts. So it will go on holding that. But the problem with the capacitors are they cannot be used as a battery. That means what these capacitors go on discharging because of the leakage current. And the problem rises after this. So after some time, you'll find that the capacitor has completely discharged. So whatever you have asked him to hold, the data will be vanished off or will be changed. So what we do for that is we go on refreshing the data. That means whatever we have asked him to hold, whatever data we have stored in DRAM, again we have to give the same data to a DRAM. That is called as a giving that data after every interval is called as a refreshing. So that refreshing is necessary in DRAM. Then why not to use SRAM? Why to use DRAM? Again, there is an advantage of DRAM, and that advantage of DRAM is it takes less space because in if you see SRAM, one bit requires a D-type flip-flop. Flip-flops are made again by the gates, and gates are again made by 2, 3 MOSFETs. And because of this, the size of SRAM is large as compared to the size of DRAM. As they had to include all this SRAM and DRAM into one IC chip, that's why they said, okay, let us go for DRAM. And DRAM requires a refreshing. So if I go below 1 megahertz, that refreshing rate cannot be achieved and your data in DRAM will be changed. And due to that, the minimum clock frequency what you can give is 1 megahertz.
Okay.
Any other question?
Hello, sir.
Yes.
Sir, can you explain connection between PSW and DPTR?
PSW and
DPTR.
there is nothing connection between these two, but the connection is to the 8-bit data bus. Remember, so 8-bit data bus also goes to program status bus, also goes to DPTR. Actually, DPTR is made up of two registers, two 8-bit registers. One is DPH and one is DPL. So two 8-bit registers make one DPTR, which is a 16-bit. So why it is connected to 8-bit data bus? Because I can store data in DPH and I can store data in DPL. So that's why it is connected with a 8-bit data bus. Program status word is also connected to 8-bit data bus. Why? Because I can change or I can identify, I can retrieve whatever flags are generated in program status word or in status register. So it is not the connection between PSW and DPTR, but both are connected to 8-bit data bus.
Okay,
Yes.
sir. Thank you.
Any other question?
No, sir.
Okay. So anybody else with the question?
So it is a ROM require some battery power to store the code, or it
ROM requires some battery power to store the code? Yes, definitely.
if
Every
you
memory without battery is not possible. Now, normally ROMs are made with the fuses also. So if you blew the fuse, that means 0. If you keep the fuse, that means it is 1. So unless and until they are not powered up, that is, if you are not giving supply, the data you will not get or you will not receive any 1 or 0. So once it is given data, then yes, the data will remain as it is. If you in ROM, the difference between ROM and RAM is that if data is stored in both, whether it is RAM or ROM, and you switch off the power. After switching off the power for some time, again you switch on the power. In RAM, you will not find any data, but in ROM, you will find the same data which you have stored. That is the difference between RAM and ROM.
Okay, okay.
Any other question? Any other question? Okay, so I'll go to this next thing, that is um, pin diagram. This is the pin diagram. So this is a 40 pin IC, as I told you before also. There are 4 ports, port 0, port 1, port 2, and port 3. This is port 0 pins. Um, these are port 1 pins, these are port 2 pins, and these are port 3 pins. So individually there are 32 IO ports. You can access individual port pin also, and they are named as P0.0, 0.1, 0.2, 0.3, and so on for all the ports. So individually you can access each and every port pin. You can also access whole 8-bit 8 pins of port 0, whole 8 pins of port 1, similarly for port 2 and port 3 also. So the pin where they are located is given by this pin numbers. At first pin is having P1.0 and so on, it goes on. The rest 8 signals, which were EA bar, ELE, PSEN, normally this is PSEN not bar, which you have to again convert it to PSEN bar. Then RST, XTL1, XTL2, um, these pins you can use separately, just like for RST I told you, you have to connect some circuit for resetting. Across this XTL1, XTL2, you have to connect a crystal oscillator, and EA bar is external access bar. If you're not accessing external memory, then this EA bar should be connected to DCC. If you want to access external memory, then they should be connected to ground. And ALE is always used whenever you are having multiplex address data bus. Here you can see those multiplex address bus, address data bus. You have address also coming on this pins, and also the same pins are used to take in or give out data. So ALE, address latch enable, and then PSEN, as I told you. Rest these two pins, VTP and PROG bar. These two pins are not used in 8051, but they are used in higher processing such like 80C, 89C51 or 89B51 pins. They are used to program your flash memory. In those microcontrollers, there is a flash memory, not a ROM. So in those cases, we can use these two pins. Any doubts in this pin diagram? As I told you, on port 3, we are having separate pins for each and all this. RxD, TxD is used for serial communication. INT 0 bar, INT 1 bar, these are two external interrupts. T0, T1 are used by the timers to take in the counting. And read bar and write bar, these two pins are used as a control signals for data memory. So these are the signals which are added in the architecture. Um, rest anything you need again explanation, tell me. Is it clear, everybody? Any doubts, any questions in this pin diagram?
Sir, this microcontroller, which company make this one 8051?
Okay, now say this 8051 was made by Intel. What Intel did is that Intel was into microprocessor business. They were developing 885, 886, and during this time, people wanted some small applications. So they, for that small applications, they manufactured this 8051 IC, um, which is having almost similar base to 885, but um, not fully fledged 885 or microprocessor. They carried only few of its applications so that you can use this thing for small applications or dedicated applications. So they named that as a microcontroller because they can be used to control something and not processing. Though it can do processing also, but not at the higher level as it is done by the 885 or 886 microprocessors. That's why they named it as a controller 8051. So after some time, they were less interested in manufacturing and doing some upgradation on 8051. So what they did is that they opened the code for 8051. That means they asked the other companies to take this code and do their own IC chip. And after that, Intel just forgot about doing any controllers, and the rest companies just like Microchip or Acmega, all this they took the code and they started manufacturing the microcontrollers, and they are into the microcontroller business after that.
Okay, thank you.
Any other question? Okay, so if there is no question, I'll go to the next part, that is the supervisory control circuits. Normally, whenever somebody asks you what are the supervisory control circuits, then I'll explain what they are. Supervisory control circuits, that means two circuits basically. One is the connection for the reset signal and the other is the connection for the crystal oscillator. These two circuits has to be there in each and every controller or processor. So that's why they are called as the supervisory control circuits. So what are these circuits and why they are used? I'll explain you. First thing I'll tell you about a reset signal, RST or RESET. This requires a active high signal. So what the circuit has is one is a capacitor and in series connected is a resistor. Across this capacitor, we are having a push button switch. So if you press this push button switch, your controller will be reset immediately. Then why this circuit is required? Instead, I would have just connected a switch and a reset directly connected here. So if I press this switch, then immediately 5 volts will be applied and your controller will go into reset. But why this circuit is required? So simply speaking, a reset. Whenever I press this reset, your controller will go into reset immediately, but will not come out of reset immediately. Remember, will not come out of reset immediately. Why? If I release this switch, immediately this reset signal will not be zero. Why it is not zero? Because whenever I have pressed this switch, your capacitor has completely discharged. And after removing this switch, that means after depressing or removing the pressing on this switch, this becomes open circuit. So capacitor initially is zero charge, but as time goes on, the capacitor will go on charging exponentially. And As it goes on charging exponentially, slowly, the voltage at this point will go on decreasing from 5 volts to 0 volts. So it will take some time to completely charge this capacitor, and that time, after that time, your controller will come out of reset. Though this time is in microseconds, but if we are forcing controller to come out of reset after some time, not immediately. Why we require this? Because controller has a facility or as a advantage what we have given him is that whenever it has started, it will immediately give address to the code memory and take in data from the code memory and start that is called as fetching and then start decoding and execution. So immediately it will start working on fetch before execute process. By the time your memory may not be ready to give out data, so it may take wrong data and process it. So to prevent those things, we provide this circuit called as a reset circuit. So have you understood this, what I said just now? Okay, so this is about the reset circuit, how and why it should be connected. So I want more time than go on increasing capacitors, microfarad and resistors resistance value. So as you increase these values, your time to come out of reset will go on increasing. If you decrease the values of capacitor and resistor, then the time to come out of reset will be reduced. So it's up to you how to design and make it in such a way that it takes some time to come out of the reset. This is about the reset circuit. Next is the oscillator, crystal oscillator. You have to connect across XTAL1 and XTAL2. Here we have connected 12 megahertz crystal oscillator. Just connecting only crystal oscillator does not work or make the purpose. Why? Because the crystal oscillator always has two types of frequency. One is a series resonant frequency and the other is parallel resonant frequency. So normally whenever it is mentioned on the oscillator, whether it is 12 megahertz, it is clearly written on the crystal oscillator. So if I want to use 12 megahertz, which comes from the parallel resonant frequency, then the serial resonant frequency should be avoided, and to do that and to make this work as an oscillator, because only crystal cannot be an oscillator, you have to connect a circuit, and that circuit connection is to give 33 picofarad to capacitors to its two ends, and the other end of both the capacitors should be grounded. Why only 33 picofarad? Because if the crystal is in the range of 1 megahertz to 20 megahertz, then we require a 33 picofarad capacitor. There is a calculation for that too, but not necessary right now. So these two capacitors are connected so that your series resonant frequency will not interfere, and secondly, this crystal will start working as a oscillator. So this is about the second supervisory control circuit, that is for the crystal oscillation. So whatever your application may be single LED glowing also, you have to connect these two circuits. Or if you are having full-fledged application where you're controlling LCD display, that time also we require these two circuits. So always your controller will not start unless and until these two circuits are provided to the controller. Have you understood?
So this crystal not understand this series and parallel resonant frequency.
Say normally crystal is made up of RLC, resistance, inductance, and capacitance. And that is the crystal is mounted on two parallel plates. And those two parallel plates make one parallel capacitance to that RLC. So there are two capacitors, one is series capacitor and other is a parallel capacitor. So because of this RLC or because of LC, it comes out that there are two frequencies. One is series frequency because of the series capacitor, and the other frequencies because of the two plate capacitor and a inductor into the inside the crystal. So because of this two, it gets out two frequencies. One is series resonant frequency and other is parallel resonant frequency. So which should be used? So normally whatever is written on the oscillator is using parallel resonant frequency because that is more stable as compared to serial resonant frequency. So to avoid or to use only parallel resonant frequency, you have to make a crystal oscillator. Now crystal is only a crystal, whereas this three components, one crystal and two capacitors, this make one frequency, one oscillator, and we have to connect a crystal oscillator, not only crystal. And that is the reason we have connected the two capacitors there.
Okay, thank you.
Any other question from anybody? Any questions? So if there are no questions, then we'll end this meeting and we'll see tomorrow the other part of that, how to connect externally, and then we'll go to the how the memory is organized or memory organization. And then after that, we'll go to the instruction set. Okay?
Okay,
Okay, sir.
Okay. Then I'll end the meeting.
sir, regarding this
Regarding,
yesterday lecture, because I joined today only,
almost I have completed yesterday's features right now.
that starting 805 futures.
Yeah, that was what was done yesterday only.
Okay. No
So,
need any extra.
no, don't need anything else. And wherever needed, I'll again take that thing because once explaining you won't be enough for you because you have been habituated to get those things once or twice or thrice.
Okay, thank you. Okay.
So anything, any questions? Okay, then I'll end the meeting now. Again, we'll see tomorrow 6.
Okay.